me ha mandado el IFISC. La carta, ya no sé qué, ya recuerdo. Estoy pensando eso.
¿Cómo? ¿Telefónica? Tienes que haber puesto algo. Tienes que haber puesto algo. Claro.
¿Sabes que aquí damos puntos o primero que tiramos? Yo creo que la camiseta está verde es para luego hacer el efecto cromo.
¿Tú crees que es una casualidad que... O sea, ¿tú realmente crees que es una casualidad que te hayan dado justo antes del seminario?
No me doy cuenta, me doy cuenta de eso. Me doy cuenta de
Bueno.
Hola, ¿qué tal?
¿TIDES? ¿Telefónica Investigación y Desarrollo?
Sí.
TID. Telefónica Investigación y Desarrollo.
Vale. So, I think also you know Esteban Moro. So he's in Universidad Carlos III de Madrid in a mathematics department. However, I mean, most of his interests are very related to the things we are doing here. In particular, the seminar he's presenting, but also he's working on the stock market, on fluctuations on assets, formation of groups. The venture, yes, right. So yeah, he's visiting us for a couple of days, and he's leaving this late this afternoon. So you want to talk with him? Just well, he's gonna be in the last row, and I'm sure you are welcome to talk on networks, diffusion on social networks, the stock market, fluctuations, and things like that. Right?
Well, thanks, Victor, and thanks all of you and IFISC for hosting me for this couple of days visit. So I'm going to present today some research we are doing together with the Telefonica Research and Development Group. Telefonica Research and Development Company, which is called TID, Telefónica Investigación y Desarrollo. This is a work mainly done by Giovanna Meritello, who is my student, but is also has a grant, a fellowship together with our university and Telefonica Research and Development, and Rubén Lara, which is the head of one of the groups there, specifically the user modeling group, whatever that means, user modeling. This is the group. And what this you can find is this.
This is still called Telefonica, it is not Movistar.
No, the company is still called Telefonica. The product is called Movistar. All products by Telefonica are for Movistar. And this is the prepping, but it's in press right now as a theory. So this is basically what I'm going to talk about this paper. So the idea is very simple: is that in the last years we have had access to data of how people communicate. Now it's pretty easy to get data about emails or telephone number or telephone communication, but also you can find instant messages or Facebook data or Twitter data. This is another project we are doing together with Jose and Victor here on Twitter data. So basically the idea is that we have data about, here for example, these are mobile phone numbers. This mobile phone number is calling this one at this time and is speaking for 2 minutes or whatever. So there's a lot of data about how people communicate. And there are two basic results or two basic approaches to study this data. The first one is topological. Is the number of people we talk to is very different. So we are very heterogeneous at the level of how many people we contact to, okay? For example, in 1 year. And this is, for example, 300,000 people in one of the mobile phone companies. You can see it's very, well, it's basically a ball of fur, but you can see that there are people that have a large degree or large connectivity in this social graph together with compared with the people, okay? So I will comment a little bit about how specifically how the uses the social network. But the other thing, and the other important thing, is that people do not communicate homogeneously. Okay, this is the main stress in this talk is about this, is that people do not talk homogeneously in time. Okay, so basically what happens is that communication, this is a time in this line, and each vertical line is a communication event. So basically what you see is that communication happens in bursts. So groups of people, Rafa, we call it in Spanish, bursts of communication events, and then there is like a waiting time to the next event, which is long. Laszlo in his book, Laszlo Barabas in his last book, burst, call it hurry up and wait. Hurry up and wait way of communication.
Each row is one telephone number?
Well, here each row is a person. And it's a communication event with anybody else.
Okay.
These people is not trying to do. But I will show you that this also happens at the level of one-to-one communication. So this will be like a link, let's say, or communication between two people.
Sorry,
Yeah.
can you explain better the thing, I mean the representation? What is the lines, the vertical lines?
So this is time, okay? And each vertical line is a communication event.
All right.
So guy A is making a call here, then is waiting, then is making another call here, etc. Okay. So the main topic of my talk will be whether, and I will show you that this is not independent of this. Okay. So the social structure, the way, the number of people we communicate is not independent of the way we communicate with these people. Okay. So this is where I'm going to go. Well, just to put in context our results, there has been many studies of mobile phone, let's say, networks or communication events. This is the paper by people working with data of ATT in the United States, in which they basically this is the topological patterns of contacts. So basically, this is the PDF of the connectivity of people in this social network. Okay. And what you see is that this a fat tail, let's say, distribution, where you can fit it to a power law or not, is a question of how you believe in the power law religion or not. But basically, it's a fat tail in which you see a large fraction of people that have a large connectivity, up to 1,000. This is 6 months data. Okay, so this guy, for example, is making call like mad, basically to make the science spark, okay? But this is also the data in a European country. This is mobile phone data. This is the paper by Ornella and Correlates, was published in 2007 with NAS. And basically you also see that there's a fat tail here. So basically this is showing you that this is very heterogeneous. This is our data. There are many lines there, but basically all of them can be fitted to a power law. Everything can be fitted to a power law, but this can be fitted to a power law quite well, and the power laws are bigger than 4, and there's the issue that maybe they are not power laws at all. I mean, because when the exponent is large, there's always the issue that they cannot be power laws. But basically, this is showing you that our data is not basically completely different from other people. In our case, we get K is actually close to 5.
And this weird baseline are just individuals, or?
Sorry?
This weird baseline that you show, the fraction of the
Well, this
individuals?
This is a matter of a finite size effect. So this is basically a line.
Individuals?
This is just one guy.
One person.
One guy divided by the total number of guys. So
And the line there? The line is this
this is a fit to a power law like this, plus a correction at a small k. Okay? So basically this, well, I mean, everything can be fitted to a power law, basically. There's the issue here that the k is actually close at is 4.6 in the case of this guy. This is 4 in our case is 5. So basically, more or less, they are more or less the same. The second thing that I will, but this is not okay. This is basically what people have done, and you can read the papers. So, but our interest is on the temporal patterns, not on the topological patterns, but on the temporal ones, the way people communicate. Okay, and there have been many studies about how people communicate. For example, this is a study of email data, and this is basically the probability of having an inter-event time for one particular person, tau, as a function of tau. Okay, so basically the time you spend between 2 emails, so the time a guy spends between 2 emails. And once again, you see that this probability distribution is heterogeneous. I mean, its fat tail is not distributed exponentially like in a Poisson process. But it's distributed, well, that's what has a theory, and other people has a theory about whether this is a power law, and then there's an exponential cutoff here, and this power law is close to 1. But again, this is a matter of controversy between different groups. This is, for example, mobile phone data, This is the group of Kim Kaski in Helsinki, Janos Kertes, and also Laszlo Barabasi. They found that the mobile phone data, also the distribution of inter-event times for, in this case, is for a particular link. So in this case, it's 1-to-1 person. You see that there is a power law here, and then it is another. The power law here is around 1, and then it closes to a power law which is around 4. Again, it might be also because it's an exponential.
Tau is the
inter-event time. So it's the
in the unit of?
Sorry.
Unit of?
Sorry. This the units of. Well, here is normalized. Okay. But here, this time is, I think, is in units of. Here is normalized by T star, which is the mean value of the group. These lines here are for different groups of different.
The ones upstairs.
The ones upstairs. Well, this is also a matter of this is one of the. Why did the referee of this paper? Because the referee of this paper complained about this 10 to the minus 2, and also this Amaral de la group complained about this 10 to the minus 2. Basically, this 10 to the minus 2, I think they divide it by, this is in minutes, and this is seconds. Okay, so emails per second. So there is a problem when you send an email, the server doesn't send the emails at once. So they put it in a queue, and then emails go, they are sent one by one by the server. And this is the problem of this 10 to the minus 2. Okay.
And the 1 week, 4 weeks, something?
Sorry?
The different lines, 1 week, 4 weeks.
Yeah, they were actually trying to see whether what is the impact of the observation window. Okay, whether this thing that you see. So basically, this thing that you see is independent. This power law here, and then the cutoff obviously depends on the time you do yours. And this is face-to-face interactions. This is another paper by Isela, which is published in the Journal of Theoretical Biology, about this is the inter-event time of contact between people in a conference. Okay, so they have this conference in which you have all these batches which are electronic, and they have this Bluetooth, whatever it is. I don't know the thing, but if you get close to someone closer than 1 meter, you register that it's an interaction. Okay, and this is the time between interactions in a conference. Okay. So you can clearly see that once again it's not distributed like exponential, but has power laws.
If it is in a conference and there is a peak at say of the order of 20 seconds or whatever, this is the same interaction, isn't it?
Yeah, I mean I don't have the particular details about this, but I'm considering this in just this region. I mean this might be also because
I mean if it is you cannot meet somebody in the space of 20 seconds, it's the same. I mean. This means that basically you are in the same conversation.
But the problem of this data is that it contains both the length of the conversation and the time between the conversations.
Yeah.
So I don't know which one of these is.
Yeah, I don't remember the actual detail, but I mean, I just bring in this paper because they found also that this distribution of times has an impact in the way information diffuses in specifically in the conference.
And from there you derive that the interaction happens in bursts from both poles? No.
Well, I mean, that's another thing. I mean, the fact that you have an inter-event distribution, which is a power law, gives you bursts. Meaning that it gives you, if you get a wind...
Burst gives you power law.
Power law gives you bursts, but burst is not the only, power law is not the only way to get bursts.
Power law gives you bursts?
Power law gives you bursts. Yeah. Look at this. I mean, you have interaction that happens. I mean, typically here, interaction that happens with minutes, and you have a large probability that the inter-event time is probability. You get a renewal process. Okay, it's a matter of how you define bursts. Okay, but if you have the picture that bursts are this picture, sorry, that you have. Inter-event times which are very small, and then a large fraction of them are very large. Okay, I can tell you that there's much more than just the inter-event in these lines. There is, for example, correlation of the inter-event times, which is not considered by just looking at the PDF. There is also the fact that it might not be also a renewal process, even if it's correlated. Okay, even you put correlation. For example, Luis Amaral and his group, they have another theory for how bursts are produced. They have a theory that there are two processes. One is in which you fire, for example, interaction, and then you have a lot of interactions, and then it decays, and there is no interaction at all. This is called the Higgs process. Okay, but power law gives you bursts, but bursts can be produced by another thing. Okay? The other thing, so one thing is this, okay, that interaction happen in bursts or cascades of events. The other thing is that most ties in a social network are not persistent. Okay? If you look at, for example, this is the paper by César Hidalgo and Rodríguez Siquel, a couple of years ago, in which they asked the following question. Okay? I observe a network for 6 months. Okay? What are the chances that I observe the same network in the following months? Okay? And, well, you can do many measures about the distance, for example, of some kind of distance or difference in the network. But one thing they monitor is the fraction of survival ties. So the fraction of ties that you observe and survive as a function of time. And we see that just after 1 month of observing a network, 60% of the ties are gone.
Sorry, what are ties?
Ties is, relationships. 60% are gone. And then it decays like, well, he says it decays like a power law here, but it goes up to 20%. So just after 1 year, only 20% of the links you observe are still there. Okay? So this is mobile phone data. Okay? This is mobile phone data. Well, there are many issues here, like people getting into and outside the network, but basically it's telling you that most of the ties you observe are not persistent. They come and go. Okay? They come and go there. There's also the same thing that was observed by Cosinet and Watts in a paper in Science, in an email. I don't want to go through the details, but basically they observe the same thing. That the networks
also is a significant part that don't they stay there. I mean, there is a significant fraction of the network that stays there.
20%.
Yeah.
Well, is that significant? I mean, I don't know.
I mean, if you think that the topology is scale-free, not talking about graphs, I mean, it's a significant fraction because if there are...
Yeah, you can ask whether yeah. I mean, we haven't done this study. We can ask whether this is the core or the minimum spanning tree or whatever of the network. I mean, the one that holds the network. Yeah. But I haven't done this research. But still, you have to consider this, that most of the details you observe are not there in the future. So basically, this is the same study, but with another different. This is they measure the correlation between networks in different time windows. Basically, they found that this is email data in a university, and also they found that the following thing is the same thing, that basically as long as you increase the time between comparisons of the network at one time and another time, the networks don't look very similar. But there's another extra thing for when we talk about time patterns, is that you think about it, most of the communication happens in groups. So at least human communication happens in groups. What I mean by this, there's a study by Eggman in PNAS in 2004, in which they study, basically this is the representation I was explaining before. This is time, and each line is a communication event. Now you see there's an asymmetry because a line up means a communication between A and B, and a line down is between B and A. It's an email. So this is a synchronous, so you have the two kinds of events. Emails from A to B and mails from B to A. Okay? And Eggman collaborators were asking the following question: If I have this time series from the time series A to B, the one from A to C and the one from B to C, what are the chances that these three time series are correlated? And way to measure this is to measure the probability that a particular day. So what they did is they took a window and they measured which is the probability, the conditional probability that you have a triangle, okay, compared to the random case. And they found that the number of triangles that appear is, well, in the random case is an exponential, and they found that here there is a large probability that you have triangles in the communication. So basically this is showing us that communication between A and B induces communication between B and C, and then from into A to C, or the other way around. I mean, there is communication. So if I call you, for example, you might call someone else just after I write for you. Or if you receive an email from someone in your department, chances are that you will send an email to someone else. Okay. So communication is correlated in the social structure. This is the same. This is a study done by people in Telefonica, which also they found that there is this is in mobile phone data. They found this kind of effects. Instead of just concentrating in triangles, they concentrate in all these motifs. Okay, and basically what they study what are the chances for these motifs to happen in communication. And the motif here is defined if there is a mobile phone from 1 to 2. And there is at one time, and there is a mobile phone call from 2 to 3. After 10 minutes, the other one was received. You have a motif, a causal motif. Okay? So these causal motifs, they study these causal motifs, compare it to the random shuffling of the timestamps, and they found that this, for example, happens 43.8% more likely than compared to the random case. Okay? So you clearly see, for example, in this case, that the calls from 1 to 2 clearly induce the calls from 2 to 3. Okay? So these are the three basic findings in temporal patterns. So the first is that communication is not homogeneous. Second is that ties are not persistent, so this is something you have to take into account. And the third is that human communication happens in groups. Basically, is that this time series is correlated to the other ones. Okay. So what I'm going to show you is what is the impact of these specifically compact patterns in information diffusion in social networks. Okay. Well, first of all, I just want transparency to remind you that the topological patterns have an impact in the way information diffuses. And this is other people call it the result by Espignani and Romualdo Pastor-Satorras, but this is basically the Feld paradox. Is that if you look in a social network, I don't know if you have done this exercise of going to your LinkedIn homepage or going to your, for example, in the LinkedIn homepage, you see that I don't know if you notice this, there's a box in which you say, there is 280 people in your network. Oh, sorry, you have 280 people as a friend, and there are 200,000 people in your network. I don't know if you right here. Okay, whatever. That is telling you first that you don't use LinkedIn, and the second thing is that there are these people that LinkedIn name in your network are next nearest neighbor. Okay, there are people that are just 2 links away from you. So 2 links away from you, basically you have 500,000 people. Okay, this is the third paradox, which is telling you that your friends have more friends than you do. Also in Facebook, if you go to Facebook, you can clearly see that you are always have a friend that have zillions of friends. And I think it's the way why Facebook works. Because you go there and you say, well, this guy has more friends than I have. I have to have more and more friends and more friends. Okay, this kind of social experiment. Basically, the paradox is the following: is that you are more likely to be friends with someone that has more friends than with someone that has fewer friends. Okay, so basically, this number, which is the number of next nearest neighbors in the social network, is basically if the network is random, apart from the distribution of connectivities, then you see that this number is given by the ratio of the second moment of connectivity divided by the first moment. As I told you, the probability distributions are fat tail, so this guy is basically in social networks, typically this guy is around 2 orders of magnitude. This one, 2 orders of magnitude. So this means that on average, you have the average connectivity of your neighbors is 100, more or less. Okay. Well, this is just to remind you that topological patterns have some issues, because if there are so many people around you, the structural properties of the network favors information diffusion. Because once you get across your neighbors, your nearest neighbors, you get to thousands of people, millions of people. Okay, and then information diffusion is favored by the structure. But I'm not going to talk about this. I'm going to talk about temporal patterns. I'm going to give you an example that temporal patterns are very important to describe information diffusion. Suppose I have the following, this is my database, okay? I have 3 calls between 3 people. I have a call from red to yellow, I have a call from red to blue, and I have a call from yellow to red. Okay? I get all my data, I compute my social network. This is my social network. Okay? And I'm going to ask you, what is the probability that a message that yellow knows gets to blue? Well, you go to this, and then, well, the jump here is, let's say, lambda, and this is lambda squared. Okay? But think about the temporal pattern. What is the chances that if yellow knows something, it gets to red? 0. There are no chances. Okay? To blue. There are no chances to get to blue. Okay? So the temporal patterns, in this case, the causality of how things occur in the social network impact the information diffusion. This is what I'm going to talk to you today. Well, the first impact on information diffusion of temporal patterns is that information travels slower. Okay? Because of this reason, I mean, there is no, suppose that there is another people connecting to yellow, and there's a longer path, let's say, from yellow to blue. Okay? So the fact that the temporal order of communication happens in this way makes this short path completely inefficient for information diffusion, but it might be another one in which you get from yellow to blue, which is for sure longer than 2. Okay? So the first impact is that information will use those longer paths, and information will travel slower in social. This is, for example, what we did. But I mean, there's another way to show it. We did an experiment of video marketing in 2009, in which we saw that the number of infected people, the number of people receiving information in a social network decreases like this, while you were expecting that if everything was exponentially, I mean, there is no temporal patterns, it will go like this red line. Okay, so just 60 days after information diffusion started, still we get people that were infected. The same was observed by Vázquez and Barabasi in 2007, but this is an experiment, this is actually a computer experiment on email data. They also found that the number of people receiving a message decreases slowly in time. The number of new people receiving a message decreases slowly in time compared to the Poissonian approximation, which is this exponential line. And also in mobile phone data, Karsai and collaborators found recently that if you simulate the SI model, which is a model for information diffusion, in which you have only 2 states, informed and not informed, in their experiments, basically everybody in the end gets informed. So this is basically one means that everybody got information. So this is like a disease propagation model. And basically what they found, there are many things here, but I just want to concentrate on this, which is this is the original data, the red one, okay? And I think this one is the one in which they shuffle the times, so they destroy the temporal patterns of communication, and they found that this is the probability of having a realization that takes TF time to get to 1, okay? This is the prevalence time. And so they found the prevalence times is larger than from the Poisson approaches. So basically, information travels slower due to the temporal patterns. Okay, but there is something else. In most of the studies,
Before you go ahead, how is this related, if it is related, to processes of anomalous diffusion in disordered systems?
okay. Well, you can get anomalous diffusion in 2 ways, if I remember correctly, by getting correlated, let's say, time increments or space increments, or you can get it by having Levy or
Cascades in disordered systems so that you will jump
yeah.
a temporal pattern.
Yeah.
I'm asking you because I thought about that, I didn't know the answer, and say, well,
Yeah.
you should know.
No, I don't know because I don't know which is the disorder in this space. I don't know.
Well, the fact that, as you said, you don't have a rate lambda, which is constant.
You may put in a random lambda or a lambda which is different from different people.
Yeah, your example, well, that's what you're saying, right? It's not.
No, but we see this at the level even of the links. I mean, people, communication of one-to-one people. So there could be that then links have different lambda. Okay, but this is precisely what I want to measure. The lambda of different links. I will show you this is specific at the PIJ. I will talk about. But I have an answer about.
Essentially, what you're saying is that this is not diffusive, but it is anomalous diffusion. It is,
No.
It is subdiffusive.
No. Specifically, in our case, we see that it's diffusion, but the diffusion constant is smaller.
It is not the exponent of the diffusion.
No. What I will show you is that in the SIL model, it is, well, diffusive. It's like the SIL model, the original SIL model, but with rescales diffusion, let's say, or probabilities initially. Let me get
Sure.
Okay, well, most of the studies about dynamics on network, I'm not talking about coevolution of networks, but most of the studies on dynamics on network use the Poisson approximation of dynamics. The Poisson approximation is usually taken because it's very good from the theoretical point of view and also from the analytical point of view, because everything can be done. I mean, you can write down differential equations. So you can write down differential equations, for example, for the C model in a random network. Basically, what is the approximation is that if you think about it, if you can take the probability that I communicates from J, this is basically given by a rate. So you put all the information about the way people communicate into the rate. And then you assume that the number of communication events per time is the rate. Well, okay? People typically assume that the rate is basically the intensity. So I take the number of calls I make per hour, and this is the intensity. So basically, if I make 5 calls, then you can put a renewal process, which is a Poisson process, and then the rate is 5 calls per time. 1 year. So, okay? So it's 5 calls. So basically, what is happening is the following: that you get a database which took you years to collect and process, okay? Has a lot of information about how people communicate. You put everything into a rate, and you coalescenize the activity. So you are basically destroying all the temporal patterns in the not only the one-to-one person, but also the correlation between them. Okay. So and actually more than that is assumed. There are more than that because communication can happen at any time. Okay. If I make a call to roll, for the first time of the year, and then we don't get along very well after the first month. If I take this for the rest of the year, I'm assuming that the link is there always, and I can communicate to everybody. So I'm not taking into account the problem that the tides can be disappearing and appearing. The second thing is that communication is homogeneous, as I was telling you, is Poissonized. The third thing is communication is Markovian. So you're assuming that the state of the dynamics is fully described as how the dynamics is right now. Okay? So you're not taking into account any non-Markovity. And causality for sure is lost. Okay? The way things happen in a social network are gone. Okay? For example, this example I was showing you, that there was no chance from yellow to blue, is lost. Okay, so what I'm going to do is to try to get back a little bit of those things which were lost by assuming a personalization of the dynamics. First of all, there are the two main objectives in this research. One is to improve the definition of the social link in dynamical networks. So what is a link? A link is a call, 2 calls, 3 calls. What does define a link? A link is a call every Saturday. A link is a call every birthday, for example. Well, there's a definition. I don't have a precise definition, but we will show you that you can improve the actual definition. And also have a better model of how to get information flows in networks. So this is our data. This is huge data. These are terabytes of data. And they are not very easy to handle. As you might guess, we have 2 countries of data, or data of 2 countries. We have what is called the CDR, which is the call detail record. Basically, in the call detail record, we have who is calling who, at what time, the duration of the call, some extra information which is not relevant for what I'm going to tell you. And this is the country in which we have more information, because we have all other metadata of people like SSH and also the postal code. And we also have free number links, which are people you name to get a discounted rate in calls. But this is not the one we are going to use, because we are going to study diffusion of information. In a large network, it will take a lot of time to get information to diffuse. So we need this longer time period. So this is the country I'm going to talk about. We have this is a social network of 23 million people and 700 million links.
What about data protection? How can you have access to all this information?
I don't have the mobile phone number. We have codes.
Which are the countries?
Sorry?
The countries.
I can't tell you.
This one.
No, I can't tell you. I can tell you, but what I can tell you is that they are very different. Cultural, but yes, I can't tell you the next.
So for a given number, you get the code, let's say.
I get a hash code. It means nothing to us.
Okay.
And also the time is so they shift the time, the initial time of the time by a random number, which we don't know.
Okay.
Okay. And these are data from 3 years ago. Okay. So that's the only thing I can tell you.
And these data are already analyzed by other scientists, or is just your job?
Well, I can tell you what is the process of querying to the database, which is we submit our code, okay, to these people. They run it in the servers, and we get the data back. So that tells you a lot about privacy. But we have a sample of the data just to compare if everything was working. And the sample of the data that we have is with this restriction. That everything is shuffled, and we don't have information. Okay? It's a painful process, okay? Just to get. So the fact that you compile, you run the program, then you fix the bug, it doesn't work. You have to be very careful. Well, regarding connectivity, as I was showing you, the people connect heterogeneously to the person. This is the data that we already presented to you, that they are very heterogeneous. There's another issue, is that links are not homogeneous. So the number of calls per link is very different. So you observe links, this is the number of calls per link, which we call intensity. It can be in the number of calls, or it can be in the direction, the time they were calling each other, I to j. And this is the probability distribution for having a link which has this intensity. Okay, the number of calls, for example, we have from number of calls equal to 1 to number of calls up to 5,000.
Here, your definition of link is that at least one phone call.
At least one phone call was observed, and we are considering only mutual links. At least you have a phone back and forth. Okay. Otherwise, you get all these people which are doing telemarketing. Okay, so the results are similar. I actually have to say that they are very similar to other countries. Okay, and another database. So the fact that this exponent is 1.33 in this fit, and the fact that the exponent is around 5, they're very similar to other countries, but this is another issue. Okay, so the first thing that we study is, as I was telling you, this heterogeneity, this burst behavior in the communication. So basically what we have is the communication between I and j. This is the same representation. So each vertical line is given by each vertical line is a communication between I and j. Okay. In order to understand information diffusion, so the first thing we study is the inter-event time, which is basically the time between events in a particular link. And this is the inset here. Okay. Basically, what we got is what Karzai and collaborators got, is that the black line is basically the PDF of these guys. Okay. And what you see, and the red curve is the one you obtain by shuffling the timestamps of the communication. So basically, what you get is that there is a large probability, much larger than the exponential, the shuffling, the Poisson, let's say, case, of getting short time inter events, and there is also a larger probability of getting larger time. So this is the hurry up and wait phenomenon, this burst phenomenon. You have a lot of probability to have shorter times and then a larger time than in the boson case. Okay? But for information diffusion, this is not the relevant time. The relevant time information diffusion is what we call the relay time, or the intercontact time. It's a time in which someone which has the information passes the information to I, and I passes to the J the information. Okay? So it's a three-body time. Look at this. This is the time, the communication between I and J, and this is the communication events between anybody else except in J and I. Okay? So the relevant time to understand information diffusion is, okay, suppose that one which is infected calls I. Okay? The relevant information to understand how information diffuses is the time between I gets infected by someone else and the next call to J. This is what we call the relay time, because I'm giving you the relay. Okay? It's the intercontact time. So it's not this quantity that fixes the whole process, not only the speed but also the probability, but it's this time which is called the relay time. Okay, what is the relay time? What is the relationship between this guy and this guy? Well, they are not independent, obviously, because the larger this inter-event time, the larger will be the tau. Okay? And the shorter the inter-event time, the shorter. But what is the relationship between the PDFs? Okay. So the relation between the PDFs is what is called, at least if you assume that they are completely independent process. I mean, the fact that I receive a communication and the event that I make a call to someone else are completely independent process. This is called the waiting time paradox. Actually, it happened to me this morning because I went to the metro here. I didn't know the time table of the metro, and I know that it's every 15 minutes. Okay, I waited 15 minutes. Okay, why is that? The reason why is the following: is that okay? So this is the same thing that we have previously. We have this event in which, suppose that this is the I to J communication event. So we have a communication event here, and the next one will happen here. So I gets infected here. So which is the time we have to wait until I communicates to J, so I can pass the information to J. Okay. Okay, so this is given by the waiting time paradox. So if we assume that the probability for inter-event times is this, then how long do we wait for the bus at the bus stop? Okay, so neglecting correlations between getting here and the next event, we get the following thing. Getting to a time interval of this length is obviously proportional to the length of the interval. Okay? So this is the length of the interval. Then we have the probability for the length of the interval. We have to divide it by the mean so that this probability is normalized to 1. Okay? So this is the probability to get this quantity here. Is the probability to get to an interval of length delta t. The next thing is the following. Okay? So what is the probability to get here or there? It is the same. Okay? So the probability is 1 divided by delta t. Okay? And obviously we have to sum for all the possible cases in which tau goes from, the delta t here has to be bigger than tau. From tau to infinity. So basically the probability of the waiting time is given by this one. But if you do the math, this goes, and basically you get the cumulative. So the probability of the waiting time is the cumulative of the probability of the inter-event time divided by the mean. Well, just one quantity, for example, which is the average time you wait at the bus stop. So it's basically this is the reasoning you will make. Is that basically the time you wait is, on average, is the half time the time between buses. But this is telling you that if you have that, like in Spain, the buses don't come exactly at the time it has in the timetable, you have a variance in the probability, and then you have the variance divided by the mean square. Okay? And this number, especially in some countries, can be very large. Okay? Well, there is a country which is mad about punctuality, which is England, of course. They published every year a report about punctuality of buses, which is 200 pages report about all over England. Okay? Between Britain. And this is the bus punctuality of what is called the non-frequent buses, which the non-frequent buses are the ones that have less than 4 buses per hour. Okay? So basically, this is the delay time. This is the probability. The probability of having a delay 0, 1, 2, 3, 4, 5, 6 minutes, etc. You can clearly see that there are some buses that came earlier, So there would be many on the hour. There is a long tail of buses that came even after 16 minutes, which I think they stopped here, but in Spain we will have to go much farther. But this long tail in the punctuality is telling you that the variance here is larger. Actually, you measure it, you can measure it, and this number is around 0.4. Okay, so that means that the waiting time is basically the one you expected times 2. So basically, it's the frequency. So in the timetable, the authorities should quote not only the mean, which is the frequency of the buses, but also the variance. Then you can do the math, and then you can see where you end up waiting the frequency of the bus and not the mean of the half of the frequency. Okay. So this is precisely what is going to happen, or where is this is the waiting time paradox. This relationship between tau and delta t, this one, okay, is the one we are going to test. If the data fulfills this one.
But in this case, the two events are not independent, right? You're most likely to call someone telling something.
Right, so we are
okay. Extra correlation.
Okay, so we are going to test it. Okay, so this is the test. So this is the real data is black. The waiting time approximation, which is this one, is blue, and the shuffle, in which I shuffle completely the data, is the red one. And forget about the inset. Concentrate on the full plot. Here you can see this is the probability distribution for this time. As a function of time, we divide it by the mean value of the interleaving time because links are very different. So some links are more frequent calls than the other ones. And here you can see this is the exponential result. So basically, if you have a shuffle, let's say a Poisson process, the distribution of interleaving times is this, and the distribution of relay times is the same one. Okay? So basically, you get the result when you shuffle. Apart from this small deviation, which is due to the circadian rhythms, so that you don't make calls by night, during the weekends or during holidays, etc. You get that in the shuffle case, everything works. So basically, the distribution of relay times is the exponential. In the case in which we shuffle this data only, so only the calls that someone makes to GI, then we destroy the correlation. Okay, and then we should get back the waiting time approximation, and we get it. Okay. We get the correlation.
You're taking an exponential, you have a log, how should I look into that? I'm getting lost with your pointer. I'm getting lost where should I look? I mean, you have an exponential distribution.
So red is the shuffle. Red is the shuffle Poisson case, okay? And then the dashed line here is an exponential, analytically an exponential. Okay? So in the shuffle case, you get the distribution of inter-event times is an exponential, and the distribution of relay time is an exponential. The same exponential. Okay? Now, we move to the waiting time approximation, which we still get the distribution of inter-event times here, but we shuffle this data here, okay? And we destroy the correlation between the two. And we get the blue line. So you see here that the blue and the black, which is the real data, coincide here. So this approximation works very well when the inter-event times are very large. But for small inter-event times, what you see is that there is more probability to get a smaller inter-event time than what the waiting time approximation tells you. And the way to explain it is because there is a correlation between this and this. So if I get a call, I have more chances to make a call, okay, to someone else. So here we have a more smaller relay times due to this correlation, and here we have larger relay times because larger I would say because of larger inter-event times. Okay. So basically, this part can be explained by correlations between group conversations, and this part here of the relay time can be explained by long waiting times in the bursts. Okay? Good. So what is the impact on this in the information diffusion? So far, I'm just describing the things. Now I'm concentrating on what is the impact of this in information diffusion. So we don't have an actual experiment here, so we don't have information diffusion in mobile phone calls, but I just assume a synthetic model of information diffusion, which is this one. This is the SIR model, in which people can be in 3 states. They can be in the uninformed, let's say, state, which is the S state. They can be infected or informed state, or they can be resilient. Resilient means that they have been informed, they have information, but they have decayed into a state in which they are no longer interested in passing over the information. Okay? So this is a model which has been applied also. This is a model for disease propagation, and also has been applied for information and rumor propagation in social networks. So the assumption is that in any call, a person which is infected can infect another one with probability lambda, and the second assumption is that with probability gamma, a person which is informed can decay to the Earth. To make things a little bit simpler, we assume that this process is not probabilistic. Okay, so specifically after t, capital T seconds, this guy receives the information, it immediately decays into the Earth. We did this because we don't want it to be being very complicated. Okay, but it can be done. It can be done to assume probabilistic decay or even power law decay or so what are the results? The results are the following. Here I'm showing you which is the size of the average size of the cascades. What I mean by cascade? So we start with an infected person, okay? Just one, which is the C. And then these guys start calling neighbors, okay? And they can infect neighbors. And then those neighbors which are infected can infect other neighbors. So in the end, we have a cascade of infected people, which eventually stops at some point because everybody has actually decayed into the recovered state, and there is no one else which is infected which can still infect other ones. Okay? So we measure the average size of the cascades as a function of time. We see there are 2 regimes. The first one, this is for very small. This is for very small lambda. Okay, we see that the real data, which is the black line, so the information gets to more people than when we shuffle the data. Okay, so the average size of the cascades is larger than for the shuffle case. This is the shuffle case in which I completely destroy all the correlations and all the inter-tiny distributions in the links. But there is another regime in which we get the opposite. We get that the shuffle data gets to more people, the information gets to more people than in the real case. Okay? And we haven't continued this line, larger values of lambda, but this difference can be large, up to 40%. Okay? So information can be, in this sense, information gets to less people than in the shuffle case. So this is what is in the left. On the right, we have a way to characterize whether there is a percolation transition here dynamically, which is by looking at the largest size of the cascades. So we do this thing for 10,000 seats, and then we monitor the maximum size of the cascade that we get. A way to monitor percolation transition is when you get from basically 0 maximum size of the cascades to infinity. Okay? And this is the way this is the point in which we get that this starts to grow up. And this line, I will talk a little bit later about what is this line, okay? Which is a theoretical result.
Last question.
Yeah.
In the case of lambda quite large, where you have this fast distribution, I guess, of data, it is true that usually the randomized case gives faster speed of communication like that panel shows, or is the other way around?
So there are 2 things. One is it's faster. So if you, for example, you fix a time, it's faster, and then the total rate
is larger.
Is larger.
But this is always the case.
Always.
So the random, without correlation, it gets faster.
It gets faster than the real case, the real data.
So it's just a confusion on the shuffling process, because you said that you shuffle just the correlation between.
No, I shuffle timestamps.
You shuffle the time, okay, but you get a link with the average time, you say. You give us.
No. I get the links still have the same number of events.
Yeah, okay. Exactly.
But now what I have changed is the distribution of inter-event times, which is exponential, and the correlation between links, let's say. The time correlation between links. Okay?
I don't see how the network changes then.
The network is the same.
So why you what? Okay.
Okay. So let me explain you how to understand this. The way to understand it is by using an argument in this paper, which I think is very nice, which is a paper in which Newman showed that you can map a dynamical process, which is the C, into a percolation process, which is a static thing. Okay? And this is what we are going to use. We are going to use this argument, the same argument, to map a dynamical process into a static process. Okay? The way it goes is the following. So, think about this. Okay? This is the same scheme that I was showing you. Communication between I and J, communication between anybody else but J and I, and then this is the time in which I get a call from someone else, and this is the next time to the following event in between I and J. Okay, and this red rectangle is capital T. So what is the probability that I infect J? Since there are two events in this window, the probability that I infect J is 1 minus lambda to 2. Let me show it to you. The probability that these two events do not carry an infection is 1 minus lambda to 2. So the probability that this I infect J is 1 minus this. Okay? It's simply, you can do the math. Okay? So the probability that I infects J after a time window capital T, this one, is given by 1 minus lambda to the number of events that in the link ij after a time t alpha. Well, the first approximation that, so this is basically what we have here. Okay? The first approximation I'm going to make is that I'm going to assume that when I'm communicating with someone, okay, most of the calls that I get in the past come randomly for this link. Okay? So basically, the calls from someone else, this has to be an I. Okay? Most of the calls from someone else to I are independent and equally probable. Okay? So that means that I can describe this probability for the link not just by one event, but for the sum of all possible events, and then I get this is the mean over all possible times in which I receive a call. And then we can move on to the probabilistic description of this. We can say that the probability that I infect J, this transmissibility, is basically given by this moment over the probability distribution of having n events in a capital T window. Okay? So this is the probabilistic way of going to this. If the process is Poisson-like, okay, then I guess you know what is the probability in a window capital T to get n events. It's the Poisson distribution. Okay? So I get a Poisson distribution, and this transmissibility, which I call it tilde for the Poisson case, is basically 1 minus e to the minus lambda rho, and rho is the number of events per unit time, the rate. Okay? So basically you see that the transmissibility in the C process, the probability that I pass an information to someone else, is simply a function of the number of calls, or intensity. And this is the reason why the Poisson process is usually used to model dynamics, because intensity gives you all. Okay? And what about other processes? What about real data? Well, in general process, we don't know. We have to know this probability distribution. Okay? Which for, I don't know, burst, for example, it can be highly involved. I mean, if, for example, you can do, for some process, you can actually do the math. But for the gamma process, for example, you can do the math. But for other, no. But what I'm going to do is to make two approximations. The first one is that lambda is very small. If lambda is very small here, you can Taylor expansion this thing, and you get that 1 minus lambda to the n is just specifically lambda times n. And then basically transmissibility is lambda times this average number of events from I to j in a time window. Okay? The other approximation I make is that lambda is very large. It's close to 1. If lambda is very close to 1, the only term in this sum that gives you a non-zero, let's say, almost non-zero value is n equal to 0. Okay? So basically you get that t ij is 1 minus the probability that is no event. Okay? So this is the average number of events in a time window t, and this is the probability that there is no event in a time window capital T, which is given by this. And this can be calculated if I have the probability distribution of inter-event times, I can calculate this, which is simply the probability from t star t capital T to infinity. Okay. But you see here that we have singled out what is the diffusion, so the epidemic process is lambda. And these quantities, this average value of this P0, are properties of communication of people. They do not depend on the process. Okay? So this is how we will explain it. So right now for time, so let me get through this. So the first thing is that, as Raul was saying, I mean, if you have correlation between these two time series, if I have a probability that if I receive a call, I make another call, then the average number of events in a link following an incoming call is larger than in Personalization case. Okay? So basically, the number of events after receiving a call is larger than in the Personalization case. Okay? So if you get back, then the transmissibility in this regime, when lambda is very small, should be greater than this. Okay? So the correlation between calls, the fact that I have conversation with other people, make the transmissibility for very small lambda larger than in the shuffle case. And actually, this is what you get in the data. This is the ratio of these quantities, okay, as a function of capital T. Sorry, I forgot to put capital T. Okay? And you get that the real data is always larger than the shuffle case. Okay? So the fact that the communication between people is correlated gives you that transmissibility is larger than the transmissibility in the case. On the other hand, for very large lambda, the only important quantity is the probability of no event. But then what happens? The probability of no event is this one. Look at this thing. The probability of no event is basically the mass of this distribution on the right-hand side. Okay? So if I put a line here, okay, the mass on the right-hand side is larger than in Personal case. Okay? So this P is larger in the real case than in the shuffle case. This is this dot. Okay? So this is basically the ratio. So this is larger than in the shuffle case, which is this one. Then I move to a line here. Well, here there is, still I can say that the mass on the right-hand side is larger than the one in the shuffle case. But here, I can even get that the mass is larger in the real case. Sorry, the mass is smaller in the real case than in the shuffle case. So I can get even to negative, so to other values. But in general, for longer times, for capital T very large, I get that the transmissibility is smaller than the transmissibility of the sample case. So this is what we get. We get two regimes. One regime in which what is important is the correlation between conversations, and I get that the information diffusion is better, or it gets farther. And the other regime is that in which I get that the real communication, because of bursts, is less efficient than the shuffle case. Okay, I don't have time to go through this, but I just the last transparency, I promise. Okay, so we have seen that the two quantities which are important are the correlation between communication of people, and the other thing are bursts. I mean, the fact that the communication is not homogeneous. Then our plan is to study how does this depend on the social structure. So if you have to communicate, think about this plot. If you have to communicate with 200 people, how do you do? You use a lot of bursts, or you do it homogeneously? Well, doing a communication with 200 people homogeneously means that you have to phone everybody, let's say, every week. You do that? With 200 people? 2,000? No, you can't do that. What do? You talk to someone now, okay, and then you wait for the next pieces, and you talk with him again in the next pieces. Okay? So this is basically what we found. This is the average. This is the average transmissibility of a link of guy I. Okay? And I'm plotting the average value of this as a function, and the conditional average of this as a function of k. So forget about this one. The red one is the shuffle case. Okay? There is still a dependence. Okay? There is still a dependence as a function of k. But look at the real data. The real data is that For people that have to communicate with a lot of people, let's say 200, the dynamical strength, the probability that they diffuse information is lower. Okay? So you can be a social hub. You can have 2,000 people. But what are the chances that, for example, I know Laszlo, what are the chances that Laszlo is going to communicate something that I know today? 0. Okay? So people that are social hubs, people that are hubs, topological hubs, are less dynamical hubs than you can imagine. Okay? Because the average transmissibility per link is lower. Okay, so this is it. And well, I did already conclusion. Sorry for getting some minutes.
Thank you, Esteban. I think there is time for 1-2 questions.
I don't know if I had to be from the climax of the seminar, but you promised a definition of a social link in a dynamical network.
Okay, I don't have a real definition, but my definition. But my definition is the following: take the real activity of people, and encode not only the intensity. I mean, don't observe a network for a month and 1 year and collapse everything. This is not working. Especially if you have to think about the dynamical process which is going to run on that process. For example, I'm always quoting this thing and you...
So your definition of the link depends on the process?
No. My definition of the link in this case depends on this process, exactly. But as
so
result,
your claim is that different networks have to be defined for different processes.
Right. I mean, if you have a process which has a time scale which is of the order of...
But that's not what you do, because you take the network of mobile phone conversations, and then you define on top of that network the process that you want to imagine.
I'm taking the C process. And then you can say, okay, what is better to describe information diffusion? The intensity or this, what we call the dynamical strength? I will bet you money that this is better.
Okay, so to summarize, a hint of how you define, you will define a social link.
In my case, I will get that a link is always present if I have communication between two people, but the strength, which is important for me, the strength of the link is given by this dynamical quantity.
So the strength of the link is dependent on the process that you want to.
Then you can say, well, if the strength is lower, is below at some level, there's no communication. Okay.
So, you have incorporated in your description lots of things that are usually neglected, so that's really nice. I think there is still one that is missing, but I don't see any chance that it can be included from the data you have. That when for example, if Maxi phones me and tells me something about the institute, and then in less than 10 minutes I phone my daughter, I am sure I will not pass this information to her. I mean, in fact,
you never know.
Well,
so suppose that Max is telling you you are fired. You will tell your daughter.
So you have said that the different process needs different networks, and there are familiar networks, there are business networks, professional networks, and I am inside many different networks. I transfer different types of information to each network, and I think there is some correlation between the infectivity, the lambda, and the type of link. And of course, from the database, we don't have this information. It's a little bit difficult, but I think this.
I think you're happy that we don't have that information.
So this is an important thing.
No, but as always, I mean,
for viral propagation of
but
it's
people
an
are
important point.
I think, for example, when you describe the network of the web, what that means, I mean, in that context.
You have many different.
You have many pages, and some pages are talking about cars, other ones are talking about webs, and many things.
Maybe you could, if you have data on these secret files, cross the analysis with some social indicators like instruction level, professional level, whatever. Social indicator can give
Well,
you
what we have done, but this is just an internal report, what we have done is try to see where differences, but this is something other people have done. Whether there is a difference in the structure of the network, if the ego network, let's say, around some person, depending on whether the person has some age, sex, gender, there are some very, very nice differences, and also geographical. So there are differences. Okay. So this is telling you that we are considering that the whole network.
Just tell the question of Emilio, I mean, information, which kind of information can be in some way revealed with some social.
For example, I can tell you is that communication between, I don't know if this is politically correct, the communication between two women is less bursty than between two men. In the sense that the average inter-event time for the same number of events is larger for men than for women. There are differences.
Yeah,
but we are considering that everything is homogeneous. The same
With one? Yeah. Coming to your epidemiological models, how well are they, considering that I can decide whether I forward information like Emilio does, while in spreading diseases, the probability is just given by external parameters?
Well, I mean, this is a good question. I mean, this is the simplest model you can imagine about information diffusion. But of course, propensity to pass the information and also the lambda depends on the link. That's what we meant in my first case. But in this case, the SIG model is not because we want a real model of high information diffusions. Basically, the SIG model is like a probe to test which are the relevant properties of communication which affect information propagation. But it's not really a real model to explain what is happening.
Actually, I think that what he's asking is how do we implement the concept of free will in social models?
To some extent.
So I think we should finish here. So thanks again.